elliptic dilogarithms, and people find them.
Okay, thank you very much for the invitation to give a talk in this very nice conference. What I'm going to talk today has to do with some work I'm been doing with Spencer Block on the relation between something that's called elliptic dilogs and two-loop amplitude that you get from Feynman graphs. And oh yes, that works. Okay, so as you may have noticed, in physics there have been a lot of activities about amplitude computation recently, in particular from the field theory point of view, where many new techniques have been developed and have allowed us to compute a lot of processes that are useful in order to try to get properties of amplitude in n equal 4 super-Yang-Mills or n equal 8 supergravity or over supergravities with less supersymmetry. And they are based on various techniques that are either physically motivated, like on-shell unitarity method, repression relations, infrared behaviors, but as well they are based on some tools that are more from mathematical point of view, like Grassmannian symbol, as Sasha did with collaboration with his colleague from Brown. And you can even use string theory if you want to compute some amplitude. Unfortunately, today I will not really tell much about string theory techniques. But one of the important questions that one has when one computes amplitude in quantum field theory is to understand what kind of object we are getting, what kind of function are giving the expression of the amplitude in terms of the various kinematic invariant, and if there exists a basis of function one can use, and if this basis can be used in a successful way to simplify either analytic or numerical computations. So as a general comment, for an amplitude in quantum field theory is a multi-valued quantity. So in a complex energy plane, if S denotes a typical energy that you have when you consider some scattering amplitude, there is, at some point, when the energy grows, some particle production that occurs, and the quantity that you have to consider as a function of this variable that I call S here is multi-valued. It has a branch cut, and you have to take off one part of the real axis. So it's something that is very common in any quantum field theory textbook. But anyway, so the point is that you have to keep in mind, and that will come a lot. This is a recurring point of my talk, is that amplitudes are multi-valued quantities. Okay. Another thing is that is easy to picture as well, is that this amplitude will satisfy some type of differential equation. So either you can look at differential equation that you get by varying the physical quantity that are the various momenta of the external states, or by varying the other parameter that you have in your multi-loop amplitude that are, for example, the internal masses of that. So at a very naive level and superficial level, something that satisfies monodromy and satisfies some differential equations, should look like something that would like to call period. And the problem is that what kind of period are you getting? And so the point of this talk is to precisely tell you what kind of amplitude are given by period, and period of what. And so that's the main point of this talk. So there is a very good definition of period that Kontsevich and Zagier have put forward. So you can think about some period that are given by R. So you have n quantities, x1 to xn, and here you have a rational function, and the domain of integration is being given by some set of equalities or inequalities on your variable xi here. And so this is a period as defined in this paper called, with title Period by Kontsevich and Zagier. And if you are a quantum field theorist, and if you look, for example, in the book by Edison and Zuber, then this definition here looks very close to what you would get if you use the Feynman parametrization of your amplitude, and where the amplitude is expressed in terms of rational function, where you have here polynomials that are completely given by the topology of the graph. So U is the graph polynomial, and F is the second Siegmund-Zig polynomial, and later in the talk you will see some very specific examples. So I don't want to give the general construction of this polynomial, but it's something that, with Mathematica, you give a graph and you get these polynomials. Okay. So you seem to be, happy that these two definitions seems to be very close. Well, the problem is that when you, in the context of amplitude, this integral associated to a given graph in quantum field theory, you have the problem that the denominator vanishes at the point that actually intersect the domain of integration. So you have to do something, because here that will be, I will explain exactly what you have to do, but then you cannot, if you want to define correctly that integral, then you have to be careful about the fact that they are on the boundary of, on the domain of integration, vanishing point of the denominator here. And as well, this domain of integration is not closed, so it has a boundary. So in a sense, you cannot, it's not really a period in a naive way, so you have to use a generalized version of period, okay? And so progressively, I will tell you exactly what generalized mean, okay? So in quantum field theory, as you know, generally one starts, quantum field theory, you can do perturbative computation. So typically, it's good to start with tree-level amplitude, and then after having said what you get about the structure and the relations and of generic tree-level amplitude in Young-Mills and gravity, I will go to one loop amplitude, and then go to two-loop amplitude, where I will show the appearance of this elliptic D-log. Okay, so tree-level amplitudes. So I want to think about a process in a Young-Mills theory with a gauge group G, and I want to look at something that will be like, it's something like a 5-gluon process, but n-gluon process. So the rules I'm getting from the textbook Feynman rule tell me that I have to draw some graph like that. There are many other possible graphs that I have with 6 external legs, but one rule as well that I have to do is that I have to sum over all permutation of the external legs, so all distribution of the various colors. I don't know if you see it, but this is, the legs are different colors. So the total amplitude at a given number of external gluons is the sum over all the color ordered amplitude, and it's a trivial fact that actually you can already take out the data from the gauge group, that is the trace factor over all the generators of the gauge group that labels the external gluon, and you multiply by a function here that doesn't depend anymore on the data of the gauge group, but only will depend on the polarization and momenta. And I want to study actually what is the structure of this amplitude and what are the relations and what kind of object I'm getting here. In particular, because by unitarity, I know that I can always cut multi-loop amplitude and reduce to trees. I want to already have a good understanding of what happens at tree level. So already without doing anything, by the properties of the trace, the cyclicity and things like that, I know that I have n-1 factorial over 2 color ordered amplitude, independent color order amplitude here. Okay. Of course, I could do a little better by playing with the structure of the group, but I will take a different route here. So first, all these guys here are not independent, and from physics consideration, there is what we call the photon decoupling identity that says that photons that are actually in abelian theory don't couple between themselves classically. So that means if in the sum I consider that all these trace factors are unity and I perform this sum, I should get that the amplitude where this is all abelian field, that means photons here, are just 0. So this is what. So I see that there is already some linear relations between all my color-ordered amplitude with a coefficient that is 1 independent of any kinematic invariant. In order to get full-fledged relations between all my amplitude, I need to embed actually my tree-level amplitude that is in the field theory here in string theory. So I want to see that this tree-level amplitude is a alpha prime going to 0 limit of an amplitude that will be on a disk where I have my external state that are vertex operators that I'm putting on the boundary of the disk. And if I'm taking alpha prime going to 0, then I'm recovering the answer that is here. Okay? So everywhere when I will talk about something that has to do with string theory, there's a little alpha prime, and the field theory, there will be no alpha prime. And by convenience, I'm mapping my disk to the upper half plane, and so my states that are on the boundary of my disk are here on the real line. And anyway, okay, so this is, and then by using conformal invariance, I have to fix 3 points, and I decide to fix the point that I label 1 at position 0, the point that I've labeled n-1 at position 1 on the real axis, and the point that I label n at infinity. I mean, I could have taken any other values, but this is the value I take. Having done that, now my color-ordered amplitude, the string version of the color-ordered amplitude that I'm having, that I have here, is given by some integral over, I mean, the n-3 points that are free, so n-3. I have here a function that depends on the difference of the 2 points. I mean, okay. And the important factor is that there is a factor that is the difference of the point to the power of something that depends on the momenta. So this is the momenta of the external gluon, ka.kj. So this is the scalar product. Right? And since this expression is written in string theory, I have here alpha prime, so that this quantity is dimensionless. What I want to stress is that this function f that is multiplying that from which I'm giving no information at all, but that you can work out depending on the type of string theory that you use to compute that disk amplitude, will have no branch cut. It will have poles. I mean, it can have poles. Actually, generally, it has poles. But there is no branch cut at all. And the only branch cut that I'm going to get when this quantity can change sign is in this product of factors here. And this comes by just the contraction of the vertex operators, I mean, if you are familiar with the string computation. So let me tell you what happens on just a simple case. So the case of the 4-point amplitude. So I consider the color-ordered amplitude 1, 2, 3, 4. So 1 is at position z equals 0. 2 is at position z equals 1, and 4 at infinity. 1, 2, and 4 is at infinity. And 3 has to be integrated over. So this is what this thick line represents. So I'm integrating 3 between 2 at infinity. So this is the meaning of what means color-ordered amplitude 1, 2, 3, 4. Now what I want to look is that I want to look at the monodromy of this integral here when I'm going around the position of vertex operator 1 or vertex operator 2. So one way to do it is to deform my contour of integration either by going upward in a parallel plane or down, and stating that my amplitude is real. So I mean the deformation when I'm going up or when I'm going down. And if I sum the two deformations, that should give me back my amplitude. And if I do the difference, I mean, they should give me a 0. But each time x2 minus x3 minus x2 or x3 minus x1 changes sign when I'm doing my deformation, I am picking a phase factor that I have, given by the determination of my power. So I have here exponential 2i pi times something that involves the product of the momenta of the external states. So I have here a linear relation between that color-ordered amplitude, the 2 over color-ordered amplitude, times something that depends on the kinetical invariant of my theory. And what I'm saying is extremely generic. I mean, you don't even, this is true for any type of integral of that sort. And on the other side, I mean, I know that, what I said, I mean, since this amplitude is real, I mean, the imaginary part gives me another relation between the color-ordered amplitude. And here you see that there is something interesting coming on, because here I told you that there is some relation when the coefficient is 1. It was a constant. Here I'm getting some relation where the coefficient depends on the kinematic invariant, and this is some non-trivial function, some sine of alpha prime times the product of the external momentum. In general, if you do that for an n-point amplitude where you have many contours that you can deform, you will have a generalization of that expression that I have written this way. So this is the color-ordered amplitude, sum over n minus 2 permutations. And here there is a factor that we call S, that is called the momentum kernel. Depends on alpha prime, because here this relation is written in string theory, but when I will tell you that if I take alpha prime going to 0, there is the same in the field theory, where that involves the various permutation of the legs. So this is the sum over all the color ordered. And this S factor, this is this momentum kernel, is just defined as a generalization of what I showed you for the 4-point case, a product of sine alpha prime times the scalar product of the kinematic invariant. So essentially what I'm doing here is that for those who already understood what's going on, is that I have some set of amplitude that satisfy monodromy properties, and I'm writing what is the monodromy matrix that is acting on my various color-ordered amplitude. The interesting fact is that for the field theory limit that I was telling you is the limit alpha prime going to 0, I mean, I have sines of alpha prime of something divided by alpha prime. So clearly you know that, I mean, the sine of alpha prime x divided by alpha prime goes to x when alpha prime goes to 0. So the version that I have in the field theory is exactly the same, except that I just have the argument of the sinus. So in a sense, in the field theory, you will get then that this color-ordered amplitude 1, 3, 2, 4 is related to the other color-ordered amplitude 1, 3, 1, 2, 4 times just the kinematic invariant. You just forget the signs, the 2 pi and the alpha prime. And of course, I mean, there are some relation relating this guy and this guy that I can do by some other contour deformation. Right, okay. So this is one way I've been using monodromy to relate the structure of amplitude in gauge theory. So this QCD in equal force super but at 3 level, I mean, it's 3 level amplitude. I can as well do something if I want to do supergravity or gravity. So gravity involves spin 2 states, and spin 2 states you want to think, especially if you come from string theory, as the product of, you want to use product of 2 spin 1, so you want to do some, double copy version of what I have been telling you before. So you see that here, this is double line to tell you that no, I'm looking at some state that has spin 2, and the 3-level amplitude in gravity then are obtained as the alpha prime going to 0 limit of some amplitude that is on the sphere. So on the sphere, I still have 3 points that I have to fix their position, and then I have n minus 3 points that I have to integrate over. And now what I can do on the sphere is to do holomorphic factorization. So I'm separating the integral over dz as an integral over dx and dy, so that I'm getting for the blue part here something that is identical to what I was telling you before for just the gauge theory amplitude. For the green part, I am having a factor of the same kind. The only thing that you have to be careful about is that when you do the holomorphic factorization, there is some relative ordering of the various contour of integration that you have to choose, between x and y. And that was a method that was already used a long time ago by Kawai, Llewellyn, and Tai to actually express the closed string amplitude in terms of open string amplitude. And so depending actually on what you want to do, if you take, for example, the heterotic string, the f will depend only on polarization and momenta. Again, it will not have, the branch cut will only come from these factors, they will only be poles, and the j will depend either on polarization if you look at gravitons, or will depend on the color factor for the, if you do gauge theory amplitude. And the same trick as contour deformation as I did before for this integral over x and y tells me that actually the left-hand side is now expressed as a sum of the blue integral from the x. So the blue integral from the x gives me one type of color-ordered amplitude. The green integral on the y gives me another type of color-ordered amplitude. And what goes in between is the same momentum kernel as the one I just described before. So there is an optimal way to write actually this splitting of the integral and to have the minimum number of terms in this monodromy matrix that I'm putting here. But this is one example of the way you see that you can reuse actually this construction I have told you to look at objects that has to do with closed string sector and in particular for gravity. So to summarize, I mean, and to use a more compact notation, essentially what we showed is that in the Young-Mills case, the color-ordered amplitude satisfies some linear relation where the coefficient depend on the kinematic invariant and that encode the monodromy matrix that you have there. There is this, which is this momentum kernel. And as well, it allows you to express all possible n-point tree-level amplitude in gravity as, for example, this product, I mean, two color-ordered amplitudes sandwiching the monodromy matrix S, and the meaning of the notation is exactly what you see here. So you have the sum over the various permutation, and you multiply it this way. It's a matrix multiplication. Okay. So this is a case where you precisely can see by, I mean, I didn't have to get into any details of what is this little f and little j. I mean, what these relations are very fundamental to anything that has to do with tree-level amplitude in actually gauge or gravity. And as I told you, I mean, as well, this S, I didn't put an alpha prime here, although there is some alpha prime. The S is the field theory, so this is a field theory expression, I mean, relation between the various amplitudes. So what I've been doing here? So I've been doing that I've been, already mentioned, playing with what we call the monodromy property of this various integral that come, I mean, in the underlying string structure of this tree amplitude. So fortunately, I said that I want to tell you a relation between quantum field theory amplitude and periods. I mean, this is not a period. I mean, in general, this is not a period. This is a section of a local system. It would be a period if the power here is an integer or rational. But I mean, there is no reason if I want to look at a physical process that this happens. Okay. So this is one of the main points, is that what you get from by looking at monodromies of amplitude. So
can you show once again the form of S, the kernel?
Yeah. So I mean, I have to tell me a bit, maybe. So what happened is that, yes, here you have the ordered point, and you decide to pull the contour either everybody to the left or to the right. I mean, the way you split the contour, you pull to the left or the right, gives you always the same thing because of this annihilation relation I had. I mean, so, but if you pull the contour, then each time you go over a point, then you get this phase factor. Okay. Okay. So in a sense, I mean, as I told you, I mean, people that are familiar with unitarity method knows that I can always cut all the internal line of my loop amplitude, reduce this cut amplitude to some product of trees, and product of trees are this kind of local system. So in a sense, local systems are going to come here. So to get, I mean, an appetizer of what's going to happen at two loop, I will have an elliptic local system. But I can do a little better than just saying that it's an elliptic local system. I will even to tell you what is the motive behind that. Okay. So now, alpha prime going to infinity limit. Okay, that's a good question. I'm not sure what to say about that. Yes, it's a tropical limit of, but actually, Okay, I don't know. I mean, we can discuss later because, I mean, well, I prefer not to say anything that is wrong. So let me go to one loop. So at one loop, there is a very powerful theorem, I mean, physics theorem, but I think it qualifies as well as a math theorem as well, that says that if I consider a one loop amplitude with any endpoint in 4 dimensions, I can always expand it on the basis of integrals, where here the CR depends on the thematic invariant, and here are some set of integrals, and there are rational pieces, of course, because, I mean, but, okay, as long as I didn't tell you what are these integrals, this is an empty statement, but there is a basis of function that encodes the properties of this one loop amplitude. And what you essentially, actually, the reference is more for the next slide. So what you get from this work by Bernd, Dixon, and Kosover is that what you can use as a basis of integrals are called box, triangle, and bubbles. And what I have drawn on that picture are the things that are the unitarity cut that looks at the discontinuity of this function on the complex energy plane and reflects the fact that, as advertised at the beginning of the talk, this function has threshold due to particle production. So this set of functions that are, so there are boxes integral where actually you can have here many incoming momenta, and you can have massive or massless propagators, but they don't have numerator. They are just like scalar integrals. And the box and the triangle, they give you an expression that is expressed in terms of dilogarithm, LE2, that is given this way. So, okay. And the bubbles, they give you logarithm. And of course, as you expect, there's a branch cut, and these functions are defined in the complex plane when you remove alpha line. And once you have such a statement, you are very happy, because if you are, I mean, everything you want to know, all the possible integral that you want to compute are given on this website. I mean, QCD loop. I mean, here's the address if you want to look. You can put in a computer, you can use numerics, and you can just have to determine this coefficient in this integral basis. Okay? So why is this? I mean, I'm going to be very fast on one loop because, I mean, the main point of my talk has to do with the two-loop case. But why is it important? Because when you have no basis and you know it's only box, triangle, bubbles, and rational pieces, then you can characterize the properties of various amplitude in a theory by just, or you can even sometimes characterize the theory by just the property of the amplitude on this basis, in this basis. So n equal 4 super Young-Mills, the maximally supersymmetric Young-Mills theory in 4 dimensions, I mean, has only boxes. So never triangle, you never get triangles, you never get bubbles, you don't get rational pieces. N equal 8 supergravity, again, has only boxes. So that means if you compute n graviton amplitude at one loop in n equal 8 supergravity, whatever method you use, then at the end of the day, you will find that you can express everything as linear combination of objects that are these boxes. So that means you will get object function that will be given by dilogarithm with the appropriate argument. Okay, getting the appropriate argument and the way you have to combine that is maybe not an easy task, and you have to use maybe powerful method like the symbol to see actually the geometry that is behind that. But at a very impressionistic level, from what I'm going to say, is just enough. And having proven the no triangle property for n equal 8, was actually something that was noticed by Bernd and his collaborator doing amplitude. And there is a formal proof that, again, goes through string theory, because I'm a string theorist, but anyway, characterizes completely what you want to do. Okay, because now if you know that you have only boxes and then you use data from infrared divergences and things like that, you pretty much know everything. You don't need that. The most surprising thing is that, so you see, only boxes for maximally supersymmetric Young-Mills theory, only boxes, no triangle means only boxes for n equal 8, supergravity, which is the maximally supersymmetric theory. Oh, I forgot Sugra. But the thing is that what is surprising as well is that multiphoton amplitude in QED, no supersymmetry at all. If you have enough external photon lines, only has boxes. So, this is very strange way of characterizing what happens in this theory, but supersymmetry is not the only reason why you only have boxes. Okay.
But if they all have logarithms, what's the point saying that boxes?
That's fine. Yeah, of course. I mean, yes. The statement is that there are only combination of LE2. Okay. So, but it's indeed easier in a way to think them as being boxes because then you can try to look at quantities that are okay. In the case of this QED, for example, I know that I have to get an object that has no infrared divergences. I mean, infrared free, and as well, if I have enough photons, it will be UV free. So I need to look at a specific linear combination of dilogarithm that will be without infrared and UV divergences. It's easier for me to state it in terms of the boxes property than in the dilogarithm. But there's a map between the two, okay? Just the fact that. So, right, okay. Now that I've been telling you about a strong motivation of why we need to understand what is the basis and what are the fundamental properties of amplitude, I want to go to two-loop order, okay? Unless there are some questions on what I said before. Okay. So at two loops, the situation is a little more messy. So here I have put a few examples of two-loop graph that one wants to evaluate, again, in the case of QED. So, this is typically what you would think about two-loop amplitude in some particular gauge theory. So there is a question is that what are the functions that will enter into this two-loop amplitude? What exactly, is there the same statement as what I have at one loop? Does it exist, a basis of integrals? And the question is actually not yet settled. This is a very active question in the amplitude computation community. There are partial results, and so I'm not going to be able to tell you today what are the basis statement. But essentially what I want know is to tell you that there's a direct link between amplitude and period as a two-loop order, and this is what we have done with Spencer-Bloch. So in order to motivate a little bit of what is the geometry behind the two-loop amplitude, it may be not obvious, but if you think a little bit about how these graphs are being drawn here, you can see that they all can be obtained by this vacuum two-loop graph. We are here a phi cube vertex, and then I'm putting external legs. So it's a little exercise to see that all of them are being obtained this way. Okay, so this is this vacuum graph, that is this London tube type of graph, is what I need to understand. It will be the underlying structure of any two-loop amplitude I want to compute. So with Michael Green, something like 15 years ago, we found some interesting change of variable, which maps actually the measure of integration over the Schwinger proper time. So if L1, L2, L3 are the length of each of these internal lines. So the rules that you get instruct you to integrate over all this length. And this is the way you parameterize the propagator that you have in your theory. So if you do the change of variable that you call V, like this sum of product of the length, and then you can introduce a complex parameter that I call tau that is given by this. And the amazing fact about that change of variables is that from something that is purely like a field theory, you get an integral that is just integral over V, dV over V, times some power that hopefully I got right. But anyway, it doesn't matter much because I didn't tell you what is here. And the integral over tau takes a form of a one loop. The measure that you will get if you integrate on a genus 1 Riemann surface, d tau 2 over tau 2 square, the Weil-Petersen measure. And the domain of integration is this domain that is the very particular fundamental domain of gamma 0, 2 that I've drawn here. That means I have a cusp at 0, a cusp at 1, a cusp at infinity, and here the width is 1, okay? So I want to insist on the fact that, of course, I could have started from a two-loop amplitude in string theory and tried to do what I did at tree level to take the alpha prime going to zero limit. This is not what I'm doing here. I'm just staying within the framework of the quantum field theory. I'm making some changer variables. And, it's not completely, surprise. If you count the number of real parameters, you have the same, you expect that you can have something that would look like as if you map it as a genus 1 type of integral, but that shows that actually there is something interesting going on here. So we have been using this trick a lot to compute various two-loop amplitude with Michael Green, and the point is that so I want to insist that actually, okay, so this graph has an obvious order 3 symmetry when I change the label of the legs because they are just labels. And this acts as a transformation on tau that is in gamma 0, 2. So in a sense, changing the various labels of the line, acts on tau as a gamma 0, 2 transformation. But it's not, I don't have gamma 0, 2 as the full symmetry of my amplitude. So this is why, I say that this is the fundamental domain I have to integrate over, not a fundamental domain that I would have if I would have a theory that would be an integral that would be completely invariant under the full gamma 0, 2 symmetry.
Count the number of integrals here?
Oh.
Just, it's a two-loop diagram, so it has 8 integrals.
Yes.
Where are they embedded? Can I count up to 8 in this bottom integration? Or
right. Okay, I'm sorry. So,
n, for example?
I'm sorry. Okay, I didn't see it. So if for this vacuum graph, and I'm getting n equals 0, so this is just the measure I described. If I'm getting external legs, what I'm going to put is I'm going to put points. I'm going to put one leg here, one leg here, one leg here. Anyway, so I'm thinking that I'm doing as if I would do what I would do in string theory. So we'll insert external legs. So I have to integrate over the position of the insertion point on my graph. Yeah. So this is this tau integral. T integral. But the statement is that actually if I look, for example, at if I have a leg here and a leg here, between the two legs I will have the Green function that I can define on the graph. So, and essentially the form of the integral that I have here would look very, very similar to the one I would write if I would use a string theory method. So there is a connection with the tropical limit that I can get of the graph, but I don't want to discuss that now. And the main point as well is that typically when you compute at a given number of external legs, a two-loop graph, you will have what we call planar and non-planar contributions. And all these planar and non-planar contributions are just given by this single formula. It's just the fact that you have to, when you integrate over the position of your external legs, they can be here or they can be here, and that changes the topology of the graph. So you have a single formula. Now, why I'm saying that is that essentially, if it turns that the integrand here has a good form, then I can use method that I know from string theory, in particular what Boris explained about the Rankin-Zellberg method. Do some unfolding and then evaluate this integral using method that I can import from string method. But the reason why I'm showing that today is because I want to motivate the fact that what is going to be behind this the two-loop amplitude would be some elliptic curve. And so at the end of the day, although it's not obvious from what I wrote, but hopefully it will be from what I was going to say, that I'm going to get a modular form. Some almost modular form. So two-loop amplitude will involve some object that will be related to modular form. And the reason why it comes is because, I think, to my test, is because the vacuum graph on which I can build all my two-loop amplitude takes already a form that is close to what I know from string theory, where I will get naturally modular forms. I'm integrating over the, I understand. I'm integrating over the elliptic curves. So, of course, the elliptic curve that will come into the answer is not visible on that. But it's a very, very general motivation that, I mean, you will see what's going on soon. Okay, so I mean, since I want to show you something that works in all details, I mean, I will discuss a simple case, which is called the sunset or sunrise. It depends on the taste and the time of the day, I suppose, which is actually just this graph. So I have here a two-loop graph. I have a momentum, k, that comes in and comes out. I have three masses, m1, m2, m3. So the associated integral to this graph is something that I have three propagators. So here are the propagators that I'm having. L1 and L2 are the loop momenta that are circulating in each of my loops. K, the square is not positioned correctly. The square should be here. Yes. So this should be L1 plus L2 minus K, parenthesis, K square. And for a reason that purely and for the ease of this talk, I'm going to look at this integral in 2 dimensions. The advantage of working in 2 dimensions is that the integral will be finite of UV divergences and finite of infrared divergences if I have masses. Okay. Right, so I'm going to have a finite integral so that I can try to relate to some object that I described at the beginning of the talk, this kind of period that Kontsevich and Zagier discussed. I mean, for the people who think, who are, interested in what happens in 4 dimensions, this is not a big loss in a way because I can always use dimension shifting formula to lift it up. So there are recursion relations between dimensions, non-dimension shifting formula, and okay, so that's one point. So this, of course, this 2-point, two-loop mass correction has a lot of importance in QED, QCD, so I'm not the first one to look at it. And people have already given some evaluation of this integral in terms of elliptic functions. But the expression in terms of elliptic dilogarithm, is new. So, okay. So let's do a bit of the math now. So at the beginning of the talk, I mentioned this parametrization in terms of the Simonzik polynomials and graph polynomials. So in the case of this two-loop graph that I just showed, the expression is this one. So dx dy. Here there is some polynomial in x and y that depends on the masses and x and momentum, and my domain of integration is x positive, y positive. So as advertised, this is really, really in the form of Kontsevich and Zagier. Okay. So as a notation, this is a 2-form, and this is my domain of integration. So I can use homogeneous coordinate, and now I have omega that is a 2-form in P2 minus the locus of my elliptic curve, because the point where my denominator is vanishing, x and y equals 0, defines an elliptic curve. Okay. So now, and the domain of integration, if I write it again in P2, so this is x positive, y positive, z positive. Okay. So as advertised, indeed, my elliptic curve intersects my domain of integration. So if my domain of integration is the triangle here, my elliptic curve intersects at the summit of my triangles. Yeah. So this dot. Yeah. So it's a bit difficult for me to draw because actually my curve intersects as well the line, the overline, but at a negative position. I'm sorry. So anyway. So within the domain of integration, the only thing that I have to matter that is in the positive part is the intersection at the position x equals y equals 0, y equals 0, z equals 0, or x equals 0, z equals 0. So one way to cure that problem is to do a blow-up. So I just introduce a P1 here. I blow up this intersection point. So I'm converting my domain of integration that was a triangle to an hexagon. So this is my hexagon here, H. Okay? And in blue, I still have my elliptic curve here. Okay? So now I have the other problem is that actually my domain of integration, D, that was the triangle, at the boundary, so it was not in the homology of P2 minus the elliptic curve. So, but everything is solved if I go to the blow-up. So here is the blow-up, P. So in that blow-up, I have the strict transform of my elliptic curve, which turns to be the same as my elliptic curve. Actually, the blow-up doesn't touch my elliptic curve, so I'm putting a hat, but you can actually think that this guy is the same as this guy, but this is the strict transform. So in the blow-up, no, there is no more intersection between the domain of integration D and the elliptic curve. And no, if I consider the relative homology, this is in the second homology of the blow-up minus this strict transform of my elliptic curve relatively to H. H is my hexagon, so that means the triangle when I have added the 3P1 minus this part. And this is where the main point is. So I was telling you that, I should expect that at some point, Feynman integral has to be periods. Period of what? So this is period of these motifs. So just to repeat, if I had no problem with the intersection of this locus and the property of this two cycle, I would have a two form over a two cycle that would be typically a period, okay? So in a sense, this elliptic curve, there is a variation of that elliptic curve that I will study a little later, where people have studied the case where you integrate over modulus of square equal 1, modulus of y equal 1. So for those who are familiar, this is something that comes into the derivative of what is called the logarithmic Mailer measure. But if I integrate over modulus square equal 1, modulus y equal 1, then I'm getting a good period. So that will be a period of my elliptic curve. But because my domain is, as the property I described, this is not, I have to do something, but then I'm getting a period respect to this cohomology. And this is the period of this motif. And here this is my motif. No, in physics you want to vary the momentum. So in a sense, you have a set of cohomology group where you have something that depends on the external momentum. So you have a variation of Hodge structures. Okay, so this is just language, but everything is well behaved enough so that you can work, define everything. Okay, so just to recap, so I had my two-loop amplitude. The free particle cut displays actually where is the branch cut. So if you cut all the line, you solve the equation that you get. You find that actually the branch cut is at when the sum of the mass, when k square is equal at the sum of the mass square. So in a sense, my integral here would be a multi-valued function in that plane when I've taken off that semi-axis. Let me look at a very particular case just to get a feeling about what's going on. Suppose I take k squared to be 0. Then my integral simplifies because here the square is correct. So I'm getting L1 minus M1 square, L2 minus M2 square, L1 plus M2 square. And before I add my minus k here, that is 0. So if you look at it, we have two loop momentum in 2 dimensions. So I'm integrating over 4 vectors. So I could write d for k. And if you look a little closer, then you say, OK, I have seen this function before. It's a triangle. It's a one-loop triangle because in 4 dimensions. So if I call k the loop momentum, d for k, I can write it if I want, parameterize the component of k by L1, L2, d2, L1, d2, L2. And the propagators here are just given by this rule. Okay? So now, since I told you that triangles and boxes and triangles are dilogarithms, I'm getting a dilogarithm. So if I evaluate this, it's a little exercise, and you can use the symbol if you want to do it, but you can do it without the symbol. You find that the answer is the Bloch-Wigner dilogarithm function, that is the imaginary part of Li2, and this part that makes it an analytic function in a complex plane, minus 2 points. And the arguments are just the root of essentially the polynomial that comes here. So 1 minus x. Okay, so I'm getting a dilogarithm. So I still haven't seen what is the elliptic dilog, but there's an elliptic curve, then the dilogarithm. So I want to show that actually when k square. Okay. So when all the mass are the same, this thing simplifies that where I'm getting just the fact that the roots are the 6th root of unity, and I'm getting the elliptic dilog evaluated at zeta of 6. That is the 6th root of unity. So now for general cases of k square, here is the integral I want to consider. I only have time to tell about a special case, so I'm going to discuss when all the mass are the same. So I just have one physical parameter that is k squared divided by m squared. So my integrand simplifies to this thing because I have taken off the mass parameter, and here is a simple elliptic curve. And some of you may already have recognized what it is, because it is an elliptic curve. I mean, it's a family of elliptic curve where I have 4 singular fibers at t equals 0 that I described, t equal 1, t equal infinity, and the threshold is at t equal 9. So actually, this elliptic curve, the total space, give me a family of modular curve that is x16. That actually is a K3 family. So the whole family of elliptic curve is a K3 surface. So, and the reason why I mentioned that is that when all the masses are equal and the z that comes at the special value of t equals 0 is the 6th root of unity, is just to tell you that actually the family of elliptic curve that are here, x16, they have torsion point of order 6. Now, because I have this family of elliptic curve, actually in relation to what I said at tree level, I now have an elliptic local system. And the nice thing is that if I take 2 points on my domain of integration that I call H, the hexagon, and my elliptic curve, and I look at the difference, I'm getting a torsion point on my elliptic curve, blue, that is of order 6. So I know that my motif, the second cohomology group, splits off the part of the free divisor. And actually what I'm getting is I'm getting this very nice sequence that is here. So that means that my Feynman integral, that is integral over my domain of my 2 form, I will be able to push it to something that is here in this H1 by taking a residue, and that will give me the answer. Okay, so if you look at this integral, and as a physicist, for example, what you do is that you integrate over y, and you will find that there are only log poles on the elliptic curve, and that will exhibit some integral over x. That is actually the residue that is sitting here. And at the end of the day, if you do the computation, using this characterization, what you find is that you find that this integral is given by the period of this elliptic curve times some integral of some Eisenstein series, m plus n tau, where psi is a character, a sum of characters that goes from the lattice of the elliptic curve to S1. And epsilon 1 and epsilon 2 are one form that are dual to the homology basis. And there is a natural pairing here that you define here at this level that is instructing you that you have to pair epsilon 1 with epsilon 2, and this way it's antisymmetric. So, okay. So the main point I want to stress at this level is that, although this formula is not completely explicit yet, is that if you were computing a regulator in a sense of what Spencer Block has been defining something like 30 years ago, that is a map from the K2 of the elliptic curve to the H1 of the elliptic curve, you will need to be on the reals here. So that means you will have to take the real part of what is in my integral here. But I'm not taking a real part. So this is why the Feynman integral is not a regulator. And the reason why it has to be different is that, as I told you, a Feynman integral has branch cut. It has to be multi-valued. A regulator, in a sense of Spencer Block and what enters all the work by Bellinson and company, it would be involving the D function, the Bloch-Wigner function, is an analytic function. And the way you see it is that there is some real part that comes here. So how do I get now an expression for my integral that is a little more concrete? So from my elliptic curve, to my elliptic curve, I can associate a Picard-Fuchs operator. This is a very well-known curve that is already in the classification of Beauville. It's a trivial exercise to determine what is the Picard-Fuchs operator in terms of my t. I have my Picard-Fuchs operator acting on my sunset integral. I'm getting that it's not 0, but it's a d of a one form that I can integrate by part. And what I said at the beginning, that d was not closed, tells me that actually this integral is non-zero. So it's not that my elliptic curve is annihilated by the Picard-Fuchs operator. I have a source term. I have an inhomogeneous Picard-Fuchs equation. And in that case of the all equal mass, It's just a constant, -6. Could have been 1, okay, -6. No, it's an exercise to solve that. So you express now the parameter t. You see t is the up module of your x16 family of elliptic curves. So you can write it in terms of eta ratio. You can express the various period as eta ratio, where tau is, defined this way, and q is 2I pi tau, and tau is a function of t, from this relation. So this gives a mapping between t and tau. And if you perform the integral, you can solve the differential equation. What you find is, this is the end of my talk, essentially. So you find that your sunset integral are the period of your elliptic curve times the real period times an object that I call E sunset of Q. E sunset of Q is the value at 0 that I told you. So this is the Bloch-Wigner dilogarithm evaluated at 6 root of unity divided by, actually the imaginary part of zeta of 6, plus this sum, n positive, of the elliptic version of the elliptic dilog evaluated at 2 points on my elliptic curve. So I'm taking point on my elliptic curve. They are torsion points. So I have a specific linear combination of them. And by taking, and making this Q sum is that I'm making it elliptic on my curve. Okay? And I want to stress again, this is LE2, this is not D. Maybe a little, it's not very difficult to have a better form. And so what you can just show is that this object here is sum n different from 0, 1 over n squared, 1 over minus q to the n. And here there is a character. And this character is a mod 12 character. It's a multiplicative, actually, mod 12 character. And it comes from the fact that I have torsion point on my elliptic curve. Essentially, I have to evaluate my elliptic dilog at this various point on my curve. This object actually is not modular invariant. It's almost modular invariant on a gamma 1,6. So gamma 1,6 is leaving invariant my op module because I have x16 family of modular curve. But it changes by constant plus tau constant so that actually everything goes fine. So this constant is such that they go together with the period here, and when I'm acting with an element of gamma 1,6, the full integral is getting invariant. So this is this is the end of my talk. So this is a specific example of what happens at two-loop order, where you see the appearance of the elliptic curve that is underlying the two-loop amplitude in terms of this elliptic function that is this elliptic dilog. And hopefully, the method of constructing the motif are pretty general. So in a sense, I hope that can lead to some better understanding on the structure of two-loop amplitude in the field theory. Thank you.